Hello and welcome to online lecture number 11 for Chemistry 112 during the spring semester of 2020. We are still in chapter 17. In the previous lesson, we looked at one simple way of balancing redox reactions, but it only works for simple reactions. Today, we're going to look at a systematic method, one systematic method to balance a little bit more complicated, more interesting redox reactions, the so-called half reaction method. But this half reaction method hinges on this idea of half reactions. And half reactions are kind of an artificial construct of thinking about redox reactions and breaking down a redox reaction into its two parts, the oxidation part and the reduction part. We call that an oxidation means that the element loses electrons, and a reduction, an element is going to gain electrons. So the idea is we'll have an overall reaction, and we will simply divide that or break that overall reaction down into two so-called half reactions, the oxidation half reaction and the reduction half reaction. And as we'll see in this method, the idea here is that once we've broken it down into two half reactions, we are going to balance those two half reactions separately, because it's usually a little bit simpler, and then towards the end, recombine them to get our overall balanced reaction back. So a couple of quick examples of just how to take a redox reaction, break it down into two half reactions. The same two examples we were able to balance by inspection in the last lesson. So copper 2 plus ions plus aluminum produces aluminum 3 plus copper. So this is the unbalanced redox reaction. So to properly divide this overall redox reaction into its oxidation half reaction and reduction half reaction, we need to first determine what the oxidation numbers of everything in the reaction are. So we have copper 2 plus, which is, of course, plus 2. Aluminum, being an element, is 0. Aluminum 3 plus, the charge monatomic ion, is plus 3. And, of course, copper is an element, 0. So we see that copper is reduced from 2 plus to 0. And aluminum is oxidized from 0 to 3 plus. So we break this overall reaction into its two half reactions. The oxidation half reaction just describes the process involving aluminum. And the reduction half reaction only involves the process involving copper. And as we'll see in our half reaction method, once we've broken it down into two half reactions, then we'll follow a systematic approach to balance these two half reactions before recombining them. So that's one example. And then the other example is the reaction of silver ions plus elemental copper to produce elemental silver and copper 2 plus ions. And here we have silver plus monatomic ion with a positive 1 oxidation number. Elemental silver has a 0 oxidation number. Elemental copper has a 0 oxidation number. And of course, monatomic ion of copper 2 plus has a plus 2 oxidation number. So we see in this example, what's being oxidized is the copper. It goes from 0 to positive 2. Its oxidation number is increasing. So the oxidation half reaction will only involve what's happening with copper. And the reduction half reaction involves silver. So it's going from silver ions to elemental silver. So two very quick examples of how to go from an overall reaction to its two half reactions. Notice at all times, whether it's originally unbalanced or in the end balanced, we should be able to add the two half reactions back together to give us back our overall reaction. So as we said, for these particular examples, we didn't need a systematic approach to balance them both by mass and by charge. We're able to do so by inspection, but for more complicated examples, we do need some systematic method. And in this lesson, we'll talk about the half reaction method. So the half reaction method, this is a series of steps, and specifically this only applies to when the reaction is occurring in acidic solutions, and we'll see why that is here in a moment. So the first step is to break the reaction down into two half reactions, the oxidation half reaction and the reduction half reaction. We'll go through these steps, and I think as we go through it, I'll balance that latter example using this method to see that we get the same answer we got by balancing it by inspection in the previous lesson. So we're going to go back and forth in the slides back to the whiteboard. So that's the first step, and we've already have done that. We've broken down this overall reaction to 2 half reactions. The next step is to mass, in each respective half reaction, mass balance every atom except for hydrogen and oxygen. So we want to make sure that for each separate half reaction, we have the same number and type of every single atom except for hydrogen and oxygen. And if not, then we, as we do with other types of reactions, we balance them using the coefficients. So if we go back to our 2 half reactions, we have 1 copper equals 1 copper, 1 silver equals 1 silver. So that step has already been done for us. The next step is then to mass balance the oxygen by adding water. So if the oxygen atoms are unbalanced, because remember we balance everything except for hydrogen and oxygen in the second step, if the oxygens are unbalanced, then we balance them by adding water to one side or the other. And we do this steps 2 and 3, as well as the next couple of steps for both half reactions. And we do them sequentially, or we do them essentially simultaneously. So we go back to our 2 half reactions, we mass balance everything, mass balance the oxygen rather by adding water. 0 oxygens equals 0 oxygens, 0 oxygens equals 0 oxygens. We kind of a boring example, but we'll see more interesting examples in the next couple of slides. We mass balance the hydrogen ions, or hydrogen atoms rather, by adding hydrogen ions. So if we have unequal numbers of hydrogen atoms on either side of our 2 half reactions, we mass balance those by adding hydrogen ions to the appropriate side. So we have 0 hydrogen atoms on this side, which matches 0 hydrogen atoms on this side, 0 and 0. So those steps have already been done for us. And then where it actually gets a little bit interesting, at least for our case, is we then balance the charge for 2 half reactions. We balance the charge by adding electrons to one side or the other. So we want to have a charge balance at the end of step 5, which have 2 half reactions that are charge balanced. Notice that from steps 2 through 4, we mass balanced the 2 half reactions. Now in step 5, we're going to charge balance them. So now we actually finally get to do something. So we have a total charge of 0 for on the reactant side, a total charge of +2 for the product side. Remember, we're adding electrons. Electrons have a negative charge, so all I can do to balance the charge is to reduce the charge on one side. So if I'm going from, remember we have our reactants and products, then our charge. For the oxidation half reaction, it's 0 and +2. In other words, when I'm adding electrons, all I can do is reduce the +2 down to 0. There's no way I can make 0 increase up to +2. So to do that, I'm going to add 2 electrons to the product side. And by doing so, now I have +2 plus -2, 0 charge on both sides. So they're equal to one another. Do the same thing for the reduction half reaction. The reduction half reaction, you have +1 on the reactant side, a 0 charge on the product side. All I'm doing is adding electrons. So as a result, I can't make the 0 into a +1, but I can make the +1 into a 0. And I can do that by adding electrons to the reactant side and exactly 1 electron to the reactant side. As a result, then I have +1, -1, gives me 0, which matches 0. So these numbers don't necessarily have to be 0, but this number has to be the same as this number, and this number has to be the same as this number. And what's nice about this half reaction method is that if you've done all the steps up to this point correctly, the number of electrons you apply in this step, as well as where you place them, will be a check that you've done everything correctly to this point. Specifically, for the oxidation half reaction, because oxidation involves a loss of electrons, to balance the charge in this step, if everything's correct, you should have to put electrons on the product side. Likewise, because the reduction involves the gain of electrons, to balance the charge in this step, you have to be able to put electrons on the reactant side, as we did here. Not only is the placement of electrons indicative of being correct, but also the number. So notice that we had to add 2 electrons here. And the reason why we had to add 2 electrons here was because the oxidation number changed from 0 to +2. So not only did the copper lose electrons, but specifically it lost 2 electrons, which is what we had to do, which is the number of electrons we had to add here to balance the charge. Likewise, the silver from +1 to 0. It gained electrons, specifically it gained 1 electron, which is where we had to add to balance the charge. So far so good. We have everything. We have now 2 half reactions that are now separately mass balance and charge balance. Before we're now able to recombine them, we have to make sure that we don't have excess electrons running around. We don't have electrons that we haven't accounted for yet. So in other words, before I recombine them, I have to make sure that the number of electrons that I've lost in the oxidation half reaction is the same as the number of electrons gained in the reduction half reaction. And if that already is the case, then there's nothing to do here. But what's most often the case is these numbers are different. So in order to make sure these numbers are the same, I have to multiply one or both these half reactions by some factor to ensure that this number is the same as this number. So if I have 2 electrons lost, 1 electron gained, I want to make sure I have 2 electrons gained, which matches the 2 electrons that I lost. So one way I can do that is by taking my reduction half reaction and multiplying the entire reduction half reaction by 2. So once again, take my overall reduction half reaction, multiply the entire reduction half reaction by 2 in order to ensure that the number of electrons that I gain here is equal to the number of electrons lost here. So when I rewrite my reduction half reaction, I'm going to multiply my entire reaction by 2, which means I multiply all the coefficients by this factor. It becomes 2 Ag plus 2 electrons produces 2 silver. So now that's my reduction half reaction, written a different way, still balanced, still mass and charge balanced, but I wrote it this way with the factor of 2 to ensure the number of electrons that I gain is equal to the number of electrons that I lost. And then once I get this step 6, step 7 is finally combine these 2 half reactions into one overall reaction, making sure I cancel out like species. So in other words, I'm going to add this equation to this equation. And if I rewrite these 2 equations, just to remind us how we add equations together, rather, that's my oxidation half reaction. My now reduction half reaction looks like this. And if it helps, I think it's worth the time to actually rewrite them this way. Because remember, when we rewrite equations, we combine them the same way we combine algebraic expressions. 2 elements of the same type on the same side are added to one another, and then on the opposite sides, they subtract from one another. So what minimally should happen is that we should have the same number of electrons on the product side as we do the reactant side. So those necessarily have to cancel. That was the whole point of the previous step. Then what's left is 2 silver plus copper produces copper 2 plus 2 silver, which is exactly the same balance equation we got from inspection in the previous lesson. So it's a very simple example using this systematic method, but it illustrates these ideas as we go through them. And then finally, the very last step in this process, step 8, is to make sure that once we get this overall reaction, that it's balanced both by mass and by charge. And so once again, we have our 2 tables, mass and charge. This is a way of checking. We have silver, we have copper, we have 2 silver, which matches 2 silver, 1 copper matches 1 copper. And we also have our charge balance. We have a total of +2 on the product side, or reactant side rather, which matches the total +2 on the product side. So this is overall balancing reaction because it's balanced both by charge and by mass. So as an example of going through this process with a very simple example, and then we'll do a couple more that are a little more complicated, where you have to rely upon this systematic method, this time a systematic method or some other method. Otherwise, we couldn't do it by inspection alone. So that's our 8-step process. The last step is simply a way of checking our work. So this example is the one we ended with in previous lesson, where it was an example where we probably could not do it by inspection or trial and error. We need a systematic method. So if we set this up and we go through the same process of first breaking this overall reaction to 2 half reactions, and then over the next series of steps, systematically mass balancing, then charge balancing those 2 half reactions before recombining them back into the overall now balanced reaction. We have our unbalanced redox reaction. We want to balance it by the half reaction method. The first step is to determine what is being oxidized, what's being reduced. So manganese has a +7 oxidation number. Manganese over on the product side, though, has a +6 oxidation number. Sulfur in the sulfite ion has a +4. Sulfur in the sulfate has a +6. And then 2 lessons ago, we talked about how to determine those numbers. So we can see then that what's being oxidized is the sulfur. So the oxidation half reaction is just a reaction involving sulfur. So this is going to be SO3 2-. And it's helpful to kind of give yourself some space here, because we will be adding electrons and hydrogen ions and water and who knows what else to produce sulfate. And then the reduction half reaction, we're going from MnO4- to MnO4 2-. And it's very important as we do these types of processes, because we're writing equations over and over again, making sure that you keep track of all the negative charges and you don't drop negative charges, because if you do so, you won't be able to balance the equation correctly, if at all. So we go through our process. The first step is to mass balance everything, these 2 separate half reactions, by mass, except for oxygen and hydrogen. So we have 1 sulfur, which matches 1 sulfur, 1 manganese matches 1 manganese, so we're good there. The next step is to mass balance the oxygens using water. So we have 3 oxygens versus 4 oxygens. So I need to add to the reactant side 1 oxygen molecule. Over here, I have 4 oxygens, which does match the 4 oxygens, so I'm good. The next step then is to balance the hydrogen atoms using hydrogen ions. So we have 2 hydrogen atoms, 0 versus 0. So to mass balance the hydrogens, I'm going to add 2 hydrogen ions here. So now this reaction is mass balanced for all the different elements. And then over here we have 0 hydrogens versus 0 hydrogens, so we're good. And then so now each equation, each half reaction is mass balanced. Now I want to make sure they're charge balanced. So to do so, then I'm going to add electrons to one side or the other to make sure the total charge on the reactant side equals the product side for each of these 2 half reactions. So we have a total charge of -2. So we can see that. I'm just going to break it down if we need to. A -2 total charge on the reactant side. -2 plus 2 gives us a total charge of 0 on the product side. So because I'm adding electrons, I have to be adding electrons to the product side to reduce the charge on the product side. So I can add 2 electrons here. Squeeze this in. Add 2 electrons, and now I have -2 on the product side charge, which matches the -2 I have on the reactant side. I do the same thing for the reduction half reaction. Currently I have -1 versus -2. I'm adding electrons, so I'm going to add 1 electron to the reactant side to get -2, which matches -2. So now I have 2 half reactions that are both mass balanced and charge balanced, but separately. And it's not a bad idea at this point to check that they are mass balanced, charge balanced, or as we said, we can make sure that we had, in order to charge balance, notice we had to put electrons on the product side, which makes sense, and we had to add 2 electrons because it goes from +4 to +6, a difference of 2. On the reduction half reaction, we had to add 1 electron on the reactant side. Makes sense because we go from +7 to +6. Now, before I am able to combine these into one overall reaction, I have to make sure the electrons lost is equal to electrons gained, and that's not true currently. So like we had to do before, I have to multiply, in this case, my reduction half reaction again, multiply my entire reduction half reaction by 2. So when I do so, I'll just rewrite it here. I'll get then 2 MnO4 minus plus 2 electrons produces 2 MnO4 2 minus. So that's my reduction half reaction. That's mass balance and charge balance, but it's in different form because now I have the same number of electrons gained as I lost. Now I can then add my reduction half reaction to my oxidation half reaction. So if I rewrite the oxidation half reaction, I have SO3 2 minus plus H2O produces 2 electrons plus SO4 2 minus plus 2 hydrogens. As I combine these, I'm going to make sure I eliminate anything that's on opposite sides rather. Necessarily, the electrons have to cancel. And then that's everything that's common. So I just add up what I have left. So we have 2 MnO4 minus plus 1 sulfite plus 1 water molecule produces 2 MnO4 2 minus plus SO4 2 minus plus 2 hydrogens. So this then is should be my balanced overall redox reaction. And so then that very last step, then I want to make sure everything is both mass balance and charge balance. So we can do that both by mass and by charge. Because there's lots of steps here and it's easy to make mistakes. So we have 2 manganese, which matches 2 manganese. We have 8 oxygens plus 3 oxygens is 11 oxygens plus 1 is 12, which matches 2 times 4 is 8 plus 4 is also 12. And in sulfur, we also have hydrogen as well. 1 sulfur, which matches 1 sulfur. And then hydrogens, we have 2 hydrogens, which matches 2 hydrogens. So this equation as given is mass balance. We do the same thing about charge. We have reactant side and product side, total charge. The total charge on the reactant side is -2 plus another -2 is -4. On the product side, it's 2 times -2, which is -4, plus another -2 is -6, plus a +2 gives us -4. So this overall reaction is correct because it's both charge balanced and mass balanced. Another unbalanced redox reaction that we can balance using the half reaction method is this one. So we're going to first break it up into its 2 half reactions. So we have, first to be able to do that, we have to identify what is being oxidized, what is being reduced. Elemental tin has an oxidation number of 0. On the product side, this is an oxidation number of +4. So tin is being oxidized. So we say that tin is being oxidized. So it's the oxidation half reaction. And then the nitrogen then must be being reduced. It goes from a +5 oxidation number to a +4 oxidation number. So we have then NO3 going to NO2. And then, as I said, we'll go through this same series of steps to, now that we've separated 2 half reactions, we'll go through that series of steps to first mass balance and then charge balance each of these 2 half reactions separately before recombining them. So our first step is to mass balance everything but oxygen and hydrogen. 110 equals 110. 1 nitrogen equals 1 nitrogen. We're good there. The next step is to balance the oxygens with water molecules. We have 2 oxygens versus 0. So in this step, I want to add 2 water molecules so I have equal numbers of oxygen atoms. Likewise, on this side, I have 3 oxygens versus 2 oxygens, so I need to add one water molecule rather to balance the oxygens. The next step is to balance the hydrogens using hydrogen ions, H+ ions. That's why it's an acidic solution. Hydrogen ions are readily available. We have 4 hydrogen ions, so I need to have 4 hydrogen atoms rather, so I need to have 4 hydrogen ions. We have 2 hydrogen atoms, so I need to add 2 hydrogen ions. Everything at this point should be mass balanced. Then we want to charge balance by adding electrons. So currently, we have 0 charge on the reactant side, a positive 4 charge on the product side. So I need to add electrons to the product side. And so when I do so, add 4 electrons. That'll give me then a total charge of 0, which matches the total charge of 0 on the reactant side. That number should make sense because notice the oxidation number changed from 0 to positive 4. It changed by 4 electrons. For the reduction half reaction, we have currently -1 plus 2 is +1 versus 0. I need to add an electron, and I'm going to add an electron to the reactant side to bring this down to 0 as well. And that should make sense because notice that nitrogen went from +4,5 to +4, a difference of exactly 1 electron. Before I recombine these, I have now 2 mass and charge balance half reactions. Before I recombine them, I have to make sure that this number is the same as this number. They're currently not. In order to make sure they are, I need to multiply my entire, once again, my reduction half reaction gets multiplied. The entire reduction half reaction gets multiplied by a factor of 4. So I multiply 4 times all these coefficients. So when I do that and rewrite it, our reduction half reaction becomes 4 electrons plus 4 NO3 minus plus 8 hydrogen ions produces 4 nitrogen dioxide molecules plus 4 water molecules. So it's still mass and charge balanced, but now I've just scaled everything up by a factor of 4 to ensure the number of electrons consumed in the reduction half reaction are the same as electrons produced by the oxidation half reaction. If I then add that to my oxidation half reaction, just to rewrite it, and it helps to kind of line up the arrows, keeps us from making silly mistakes. So 10 plus 2 water molecules produces 10 4 oxide plus 4 hydrogen ions plus 4 electrons. So necessarily when we add these 2 equations together, the electrons have to cancel. That's a requirement of this process. But notice other things will cancel. So not only are the electrons canceling, but notice that we have 2 water molecules on the reactant side here, and we have 4 water molecules on the product side here. So these 2 water molecules will cancel 2 of these 4 to leave me with just a net of 2 water molecules on the product side. Likewise, notice with the hydrogen ions, we have 4 hydrogen ions on the product side here, 8 on the reactant side here. So these 4 will cancel 4 of these to leave me with a net consumption rather of 4 hydrogen ions. So not only, so electrons are fully consumed, and then there's a net consumption of some of the water molecules as well as some of the hydrogen ions. So then what's left will be 10 plus 4 NO3 minus plus 4 hydrogen produces 1 10,4 oxide plus 4 NO2 plus 2 water molecules. So this is what I expect to be my overall both mass and charge balance reaction. And to quickly prove that in that very last step, it should be both mass and charge balanced. So with mass, we have reactants and products. And we have 10 nitrogen, oxygen, and hydrogen. So we have 110, 110. Nitrogen is 4 and 4. Oxygen is 12, and 2 plus 8 is 10, plus another 2 is 12. And hydrogen is 4 and 4. So everything's mass balanced. And then by charge, we have -4 plus 4, 0 charge on the reactant side, 0, 0, 0, 0 charge on the product side total. So it's both mass balance rather, and charge balanced. And then if we are actually in person, I would give everyone several minutes to work on an example like this on your own. So I encourage you to kind of replicate the same experience, to pause the video, test your understanding of what we talked about up to this point, and try to go through those 8 steps on your own to see if you can balance the equation on your own. And then you restart the video, and then we can go over the answers. Okay, so we have our overall reaction, and we want to balance it using the half reaction method. The first step, as always, is determine what is being oxidized, what is being reduced. We have elemental iodine, so its oxidation number is 0 by definition. We have iodate, its oxidation number would be +5. So you say iodine is being oxidized. So it went from I2 to IO3 minus, and then OCl minus. The chlorine has a +1 oxidation number, and over here it has a -1 oxidation number, a monatomic ion. So the chlorine is being reduced. So those are two half reactions, currently both unbalanced, both by mass and by charge, at least potentially. Now we go through our process. So the first step is to mass balance everything but hydrogen and oxygen. We have 2 iodines versus 1 iodine. So finally, we have something to do here. We need to mass balance the iodines by changing that coefficient to a 2. Now I have 2 iodines, matches 2 iodines. 1 chlorine matches 1 chlorine, so nothing to do for the reduction half reaction. Next step is to mass balance the oxygen using water. So we have a total of 6 oxygen atoms on the product side. So I therefore need a total of the same number of water molecules on the reactant side. So 6 water molecules on the reactant side to mass balance the oxygens, 6 and 6. 1 oxygen versus 0 oxygens. So I need just 1 water molecule on the product side. And then we mass balance the hydrogen atoms using hydrogen ions. 12 hydrogen atoms versus 0. So I need the equivalent number of hydrogen ions. 2 hydrogen atoms, so I need the equivalent number versus 0, so I need the equivalent number of hydrogen ions. So now my 2 half reactions should be mass balanced. I then want to charge balance them with adding electrons. So looking at our charges, current charges for the oxidation reaction and half reaction and the reduction half reaction. We have 0 charge on the reactant side, 0 plus 0, and we have -2 plus 12, or a total of +10 on the product side. So to charge balance this oxidation half reaction, all I can do is decrease the charge on one side or the other. So all I can do is decrease the +10 down to a 0. And that will require a total of 10 electrons. So I'll try to squeeze in 10 electrons here, which will give me 0 charge, total charge on the product side, which matches the 0 charge I have on the reactant side. And then for the reduction half reaction, we have -1 plus 2, a +1 total charge on the reactant side versus a -1 total charge on the product side. And I can reduce the +1 to a -1 by adding 2 electrons to the reactant side, which will give me -1, -1 total charges. So they're balanced. Good idea is to check everything so far makes sense. Notice I had to add electrons to the oxidation half reaction, which I should always have to do. And notice I had to add 10 electrons, which at first may not make any sense because iodine went from 0 to +5. The iodine atom lost 5 electrons. Why do we need 10 here? Well, we need 10 because overall there's 2 iodines involved. So each iodine needs to lose 5 electrons each. Because we have 2 of them, it gives us a total of 10. And then with the reduction half reaction, it went from +1 to -1, a difference of 2 electrons. So now we want to, before we are able to recombine these reactions and add them together, we have to make sure that the number of electrons that are gained in the reduction half reaction equals the number of electrons lost in the oxidation half reaction. So to do so, notice that I need to, again, multiply my reduction half reaction. That won't always be the case, but it has been the case in these examples. Multiply by 5, so that 5 times 2 gives me 10 to match these 10. So I do that, and then we rewrite the equation. The reduction half reaction in preparation for adding these 2 equations together, I get 5 OCl minus, and you may want to make sure that you keep that separate so you don't interpret that as 50 chloride ions. Very easy to do. 5 times 2 is 10 hydrogen ions. 5 times 2 is 10 electrons. Produces 5 times 1 is 5 chloride ions, and 5 times 1 is 5 water molecules. So that's my reduction half reaction. Then I add that to my oxidation half reaction. So if I try to line the arrows, we get 6 water molecules plus 1 iodine molecule produces 2 iodate plus 12 hydrogen plus 10 electrons. And then we add these together. We necessarily have to cancel out electrons. That has to be the case. But then I look for other things. And most commonly, it would be hydrogen ions and or water molecules. So we have, for hydrogen ions, we have 10 hydrogen ions on the reactant side versus 12 here. So these 10 will cancel 10 of these to leave me with just 2. It's a net production of just 2 hydrogen ions. With water molecules, we have 5 versus 6. So these 5 will cancel 5 of these to leave me with just 1. So when I rewrite everything in kind of the same form, we get I2 plus 5 OCl minus plus the 1 remaining water molecule produces 2 IO3 minus plus 5 Cl minus plus the remaining 2 hydrogen ions. So we have what should be an overall balance equation. And once again, to prove that by checking to make sure it's balanced both by mass and by charge. So by mass and by charge. If you don't have time to check to make sure it's both mass and charge balanced, it's probably better to check it's balanced by charge, because balancing by charge is faster to calculate and it's a little bit more reliable indicator that everything is correct. It's more likely if you make a mistake, it's going to be reflected in a unequal charge balance. But just to be complete, we have iodine, oxygen, chlorine, and hydrogen. 2 iodines matches 2 iodines. Oxygen, 5 oxygen plus 1 oxygen, 6, which matches 6. 5 chlorines matches 5 chlorines. 2 hydrogens matches 2 hydrogens. So everything is mass balanced. And then total charge balance, we have 5 times -1, a -5, a -2 plus a -5 is a -7, plus a +2 also gives me -5. So this equation is correct because it's both mass balanced and charge balanced. So in those examples, we've illustrated that in 8 steps, we can balance any redox reaction in an acidic solution. The first step is to break into 2 half reactions. We then separately balance those 2 half reactions by following the next series of steps before recombine them to give us our overall balance now, redox reaction, balanced both by mass and by charge. But strictly speaking though, that method only works if the reaction is done in acidic solution. So notice as part of that process, we had to employ hydrogen ions as either reactants or products. And in acidic solutions, hydrogen ions will be plentiful as reactants or products. In basic solutions, though, that's not necessarily going to be the case. So the half reaction method for basic solutions, and you'll always be told whether it is an acidic or basic solution to balance it in. What's nice about this method, though, is that of all the steps, there's only one additional step that we have to worry about. In other words, how to balance these redox reactions by the half reaction method in basic solutions is almost exactly the same as the method we just employed to balance these redox reactions in acidic solutions. So notice the first 7 steps are exactly the same list. Break into 2 half reactions, mass balance everything but hydrogen and oxygen, mass balance oxygen and water, mass balance the hydrogen by adding hydrogen ions. So this is temporary insanity. This is just part of this process. We'll fix this a little bit later. Mass balance the charge and electrons, make sure the electrons gain equal electrons lost. You can combine the 2 half reactions to 1 reaction. So step 7, even though this reaction is done in a basic solution, we are balancing it as if it's being balanced in an acidic solution, as if it's taking place in an acidic solution. The only additional step here is that because it is a basic solution, because the pH is relatively high, we don't have excess hydrogen ions. If it's basic, we have excess hydroxide ions. So this step 8 is to, once we get a balanced acidic solution reaction, we then add hydroxide ions at both sides to cancel out the hydrogen ions. Hydrogen plus hydroxide gives us water, and then we cancel out excess water if needed. And then finally, we check that it's balanced by mass and charge. And as before, I think it's best to illustrate these steps, illustrate these rules, especially this additional rule here with examples. So we have this example of a redox reaction that we're assumed takes place in a basic solution, and then we're going to balance it by that method we just saw on the previous slide. So everything's the same up until we get our overall reaction, and then we add hydroxide ions to cancel out those hydrogen ions that are maybe still left in my redox reaction. So as before, we want to first identify what is being oxidized, what's being reduced. So ClO minus, as we saw in the previous example, chlorine's +1, chloride is -1. So we have our two half reactions, our oxidation half reaction and our reduction half reaction. And then chromium is going from a +3 oxidation number to a +6 oxidation number. So chromium is being oxidized, chlorine is being reduced. So we write that in two half reactions. Chromium is being oxidized. Be careful with our charges and our subscripts and everything else. And chlorine is being reduced. And then we go through our process. That first step is to mass balance everything but oxygen and hydrogen, 1 chromium, 1 chromium, 1 chlorine, 1 chlorine. Next step is to mass balance the oxygen using water. We have 4 oxygens, which balances with 4 oxygens. 1 oxygen, 0 oxygen, so we add 1 water molecule to the product side here. Next step is to mass balance the hydrogen atoms with hydrogen ions. 4 hydrogen atoms, so therefore we need, versus 0, so we need 4 hydrogen ions. 2 hydrogen atoms, so we need 2 hydrogen ions. And then now everything should be mass balanced. Now we want to charge balance both half reactions. We have a -1 on the reactant side versus a -2 + 4, which is a +2. So to balance that, I need to reduce this +2 down to a -1. I can do so by adding electrons, and specifically I need to add 3 electrons to give me a -1 on the product side total charge, which matches the -1 I have on the reactant side. Likewise, for the reduction half reaction, we have -1 plus a +2, which is +1 versus a -1. So I can reduce the +1 down to a -1 by adding 2 electrons to the reactant side. So now both half reactions are now mass balanced as well as charge balanced. As a check, notice that we had to add 3 electrons to the oxidation product side, which makes sense. And it's 3 because it went from +3 to +6, a difference of 3. We had to add 2 electrons to the reactant side here because it's a reduction half reaction, so electrons are consumed. And we had to have 2 because the difference in chlorine's oxidation number was +1 to -1 is also 2. So those numbers all make sense. Now, before we combine these, we have to make sure that the number of electrons produced is the same as the electrons consumed, 2 versus 3. They're not the same numbers. So in this case, I need to multiply both half reactions by a different factor. So you can think about 2 and 3. The lowest common multiple of 2 and 3 is 6. So how can I ensure I have both 6 electrons produced and 6 electrons consumed? I can do so by multiplying my reduction half reaction by 3 and multiply my oxidation half reaction by 2. So when I do that, my oxidation half reaction becomes 2 chromium hydroxide complex produces 2 CrO4 chromate plus 8 hydrogen ions plus 6 electrons. That's my oxidation half reaction. My reduction half reaction is going to be 3 times, so 3 times Cl minus plus 6 hydrogens plus 6 electrons gives me then 3 Cl minus plus 3 water molecules. When I combine these, I have to at the very least be able to cancel out my electrons, which I do. And then I look for other common species, such as, for example, hydrogen ions in water are most common examples. We have 8 hydrogen ions versus 6. So these 6 cancel out 6 of these to give me 2 remaining. And then we have water molecules here, but we don't have any water molecules here. So when I add these 2 equations together, we'll get 3 ClO minus plus 2 CrOH4 minus, and gives me then 2 CrO4 2 minus plus 3 Cl minus plus 3 waters plus 2 hydrogens. So this would be the final answer if this reaction took place in acidic solution. It should be mass balance and charge balance. But because it's a basic solution, we're not done. Because in a basic solution, we're not going to have excess hydrogen ions produced. In a basic solution, they're going to be quickly consumed. They're quickly going to react with an equivalent number of hydroxide ions. So the additional step here is we balance everything as if it were done in a acidic solution. And then to however many hydrogen ions we have, either in the product site or reactant, we add the same number of hydroxide ions, in this case 2, to both sides. And the reason why we have to add it to both sides, because if we don't, if we just add it to this side, then that will upset what I've worked so hard up to this point to do, to mass and charge balance this reaction. So I add hydroxide ions, in this case 2, to both sides to ensure that I still have a both mass and charge balance reaction. When 2 hydrogen ions react with 2 hydroxide ions, this would give me 2 water molecules. Hydrogen ion plus hydroxide ion gives us water, so 2 of those gives me 2 water molecules. So notice we have 3 water molecules plus 2 water molecules. They will combine to give me then 5 water molecules. So if I rewrite this one more time, we'll get, it gets pretty long. We have our 2 hydroxide ions on the reactant side, plus 3 ClO minus, plus 2 CrOH4 minus, produces 2 CrO4 2 minus plus 3 Cl minus, plus 3 water molecules plus 2 water molecules, for a total of 5 water molecules. So this then should be my both charge and mass balanced overall reaction in basic solutions. But I want to check it because there's lots of room for error here. So by mass and then by charge, we have reactants and products. We have oxygen, hydrogen, chlorine, and chromium, which are kind of off the scale here. And then, of course, charge, reactants, and products. So we have oxygen, we have 2 plus 3, it's 5 oxygens, plus 8 gives me 13 oxygens. 8 plus 5 also gives me 13 oxygens. Hydrogens, 2 plus 8 gives me 10 hydrogens, and 5 times 2 gives me 10 hydrogens. 3 chlorines matches 3 chlorines, and then chromiums, 2 chromiums matches 2 chromiums, and then the total charge, we have -2 plus a -3 is -5, plus another -2 gives me -7. And then on the product side, we have -2 times -2 is -4, plus a -3 gives me a -7. So this reaction is complete, is correct, because it's both charge and mass balanced. And finally, we'll do one more example of illustrating how to balance these reactions in a basic solution. All right, so once again, this would be a class example. So I encourage you to take some time, pause the video, and try to balance this reaction by yourself in basic solution. So follow those same 9 steps that we did for the previous example. So this is our reaction. We want to first identify what is being oxidized, what is being reduced. So we have manganese, a monatomic ion, so the charge is the same as its oxidation number. Manganese in this compound, though, would have a +4 oxidation number. So it's the manganese is being oxidized. And this is, I think, a little bit simpler example than the previous one. For the reduction, as we saw before with hydrogen peroxide, oxygen has a -1 oxidation number here, and water has its more typical -2 oxidation number. So oxygen has been reduced. So we have H2O2 going to H2O. So those are two unbalanced half reactions, and then we go through our process. So first, mass balance everything but hydrogen and oxygen, 1 manganese, and 0, 0. So we're good there. Second step is to mass balance the oxygens using water. 2 oxygens, 0. So I add the same number of water molecules. Now it's 2 and 2. 2 oxygens versus 1 oxygen. So I'm going to add an additional water molecule to give me a total of 2 oxygens, 2 and 2. Next step is to mass balance the hydrogen atoms by adding hydrogen ions. 4 hydrogen atoms to 0, so I add 4 hydrogen ions. We have 4 hydrogen atoms versus 2, so I need to add 2 hydrogen ions. So at this point, these two half reactions should be mass balanced completely. Now we want to charge balance them. So we have our reactants and products. We have a total of +2 charge on the reactant side, a total of +4 charge on the product side. So I need to reduce the +4 to +2, and I can do so by adding electrons, specifically adding 2 electrons. If I add 2 electrons to the product side, I now reduce my product side total charge of +2 to match the +2 charge, total charge I have on the reactant side. You see that number makes sense because notice that I'm losing electrons in an oxidation process, and specifically I lose 2 electrons because the oxidation number difference in manganese went from +2 to +4, a difference of exactly 2. For the reduction half reaction, we have +2 total charge on the reactant side versus 0 on the product side. So all I can do is reduce charges. I can reduce charges by adding 2 electrons to the reactant side here to give me 0 and 0. So now I have 2 half reactions that are both mass and charge balanced. I'm ready to combine them, but before I combine them, I have to make sure the number of electrons consumed is the same electrons produced. Finally, in this example, we do have an example where the numbers are the same, so there's nothing to do here, except just rewrite the equations as is to make it easier to add, because the number of electrons consumed here is already the same number of electrons produced. So I just rewrite them, my 2 half reactions, just to make it simpler to see what's going on when we do add 2 equations together. Oxidation is Mn2 plus 2H2O produces MnO2 plus 4 hydrogen ions plus 2 electrons. Reduction is going to be hydrogen peroxide, 1 hydrogen peroxide plus 2 hydrogen ions plus 2 electrons gives me H2O plus H2O, which is 2 H2O. Just combine those into 1. I'm ready to add the 2 numbers together, 2 equations together rather. What has to happen is the electrons produced has to be the same as electrons consumed, so they have to cancel each other out at this stage. And then we have 4 hydrogen ions versus 2, so these 2 will cancel 2 of these to leave me with 2. And then we'll see that these 2 water molecules will cancel out with these 2 water molecules to leave me with 0 water molecules. So my process so far would be Mn2 plus H2O2 produces MnO2 plus 2 hydrogen ions. So this would be my answer if this were done in an acidic solution, because it is mass balanced and it's also charge balanced. But this is not an acidic solution, it's a basic solution. So my next step is to eliminate the hydrogen ions by adding an equivalent number of hydroxide ions to both sides. So notice we have 2 hydrogen ions on the product side. So I'm going to add the same number 2 hydroxide ions to the product side as well as to the reactant side. So notice when I do so, 2 hydrogen ions plus 2 hydroxide ions produces 2 water molecules. So when I rewrite everything, what we're left with then is this reaction, this equation, 2 hydroxide ions plus Mn2 plus hydrogen peroxide produces MnO2 plus the 2 water molecules that were formed when I add the 2 hydroxide ions to the 2 hydrogen ions. So this should then be my both mass and charge balanced redox reaction. Finally, to check it, I'm going to check it for both mass and charge balance. So we have reactant side and product side. We have oxygen, hydrogen, and manganese. So we have 2 oxygens plus 2 oxygens, 4 oxygens, 2 oxygens, 2 oxygens, 4 oxygens, 2 hydrogens plus 2 hydrogens, 4 hydrogens, 4 hydrogens, and 1 manganese and 1 manganese. So everything is mass balanced. And then finally, charge balanced, we have -2 plus +2 is 0. 0 plus 0 gives me 0. So I have a both mass and charge balanced overall redox reaction that was balanced if the reaction is taking place in a basic solution. So with this method, just a quick review, you follow almost the same series of steps regardless of whether it's an acidic or basic solution. The only difference is that in a basic solution, towards the end, we have to add the same number of hydroxide ions as we have hydrogen ions in this equation to both sides. And that's one very common mistake students make, is they add to one side and they forget that they also need to add the same number of hydroxide ions to the other side to ensure you maintain that same both charge and mass balance that you work so hard to get to that point. So this finishes with our sort of introduction to the half reaction method. This is the method that the textbook goes into detail with. This is if the homework talks about specific questions regarding balancing a redox reaction, this is the method that it's going to refer to. But in the next lesson, we'll introduce a different method. A method that's, I think, not as popular these days, but if you're good at oxidation numbers, if you're good at very quickly and efficiently determining these oxidation numbers, this other method called the oxidation number change method makes balancing these redox reactions a lot more efficient, a lot faster. But it relies very, very fully on being able to determine these oxidation numbers not only efficiently, quickly, but also just as importantly, accurately. So if you watch the video and it's harder for you because you're not quite as good with oxidation numbers as you should be, then you can always fall back to this method and still get the right answer. It's just going to maybe take you a little longer. So we'll probably go through the same examples we did for in this video. We'll do the same examples with the other method, and then you can compare for yourself and decide which one is better for your efficiency and for especially your accuracy.